brakes offer the most advanced braking technology for today's modern aircraft. Let's begin by taking a close look at a typical multi-disc carbon brake. The brake's major components are the brake frame, consisting of the torque tube
No, this stuff is really good. They have
and the heat sink, made up of alternating, rotating, and stationary carbon discs. The torque tube is the brake's foundation. It's usually made from high-strength steel and is used to transfer the frictional forces created within the heat sink into drag forces to stop the aircraft. The heat sink consists of alternating, rotating, and stationary discs. The rotating discs are driven by the wheel of the aircraft. The stationary discs are restrained from rotating by the keys of the torque tube. The piston housing is made up of forged aluminum and applies the squeeze force to the heat sink. When hydraulic pressure from the brake pedal actuates the pistons in the housing, the stationary and rotating discs are squeezed, creating brake heat and the drag forces that stop the aircraft. Heat is a natural byproduct of braking action and affects carbon brake wear in a rather complex way. To understand the causes of wear in carbon brakes, let's start by taking a close look at what happens between the discs during braking. Every time the disc surfaces rub against each other, carbon material is removed. At first, large particles wear off and remain in the interface between the two discs. These act like an abrasive sandpaper affecting both surfaces. As these large particles grind down, they continue to remove material, but begin to generate film-like debris. This debris acts like fine sandpaper and inhibits the formation of the large abrasive particles, thus reducing wear. Large abrasive particles can form at any time, but are most destructive when the brake is at a cooler temperature. When the brake is cool, the process of wearing down the larger particles is slow, and the particles cause more wear before they erode into a fine film. These bar graphs show the relationship between brake disc temperature and carbon disc wear. Notice, as the brake begins to heat up, carbon disc wear increases dramatically. The maximum wear for ABS-C carbon occurs at approximately 150 degrees centigrade. Once the carbon discs are heated above this temperature, wear rapidly decreases. During aircraft operations, the temperature range in which the high wear occurs is associated with the taxi out or cold taxi event. 79% of the total carbon brake wear occurs during the cold brake taxi out phase. The landing generates 19% of the total carbon brake wear. The taxi in or hot taxi generates an insignificant 2% of the total carbon brake wear. To better understand the wear rate in the taxi out sequence, ABS-C conducted several laboratory simulations. In the initial test, we used two different taxi stop speeds, but the same number of taxi stop events. Interestingly, the test with the higher taxi stop speeds resulted in a very significant reduction in wear. The higher taxi stop speed with its higher temperatures caused the large abrasive particles to transform faster into the finer film-like particles. As this film develops, wear decreases. In this testing, allowing the taxiing aircraft to accelerate to a higher speed before applying the brakes heats the carbon discs quicker and shows less wear. In further laboratory testing, we looked at the number of taxi stop events to see how it affected carbon brake wear. We used 5 stop events as our base and increased the stop events by 60%, or 8 stops. The total carbon brake wear also increased by almost 60%. The results of this testing showed that carbon brake wear increases in the same proportion as the number of taxi stop events increase. Through this research and testing, we recommend the following operational procedures to reduce carbon brake wear. Avoid riding the brakes. Snubbing to control the taxi speed is better than riding the brakes. Higher brake wear always occurs when riding the brakes. Conduct the taxi out stop event at a higher speed. This will cause the brake to absorb more heat, helping to reduce carbon brake wear. For turboprop operations, we recommend that pilots use the brakes during the landing stop and not rely only on reverse pitch. The brake heat generated during the landing stop will reduce brake wear during the taxi-in procedure. Minimize the number of taxi-out stop events. Less stops equal less wear on the brakes. And finally, if your aircraft is equipped with brake cooling fans, use them only when you've arrived at the gate and are parked. Combining these operational procedures, an aircraft taxiing out is allowed to accelerate to a higher speed before applying the brakes, and also uses fewer taxi-out braking events. Obviously, with these aircraft operational procedures, passenger safety and comfort cannot be compromised in any way. In addition, external factors such as airport congestion and weather will limit your ability to implement these recommendations. However, using these techniques whenever possible will improve the wear life of your aircraft parking brakes.
Alright. Systems affected by the while. All these are pretty straightforward, and at some point I remembered what the fuel system was. Somebody asked me that last week, and I forgot what's different on the fuel system. Does anybody know offhand? Somebody told me once, and I just can't recall it. And I remembered it wasn't quite an indication thing.